Welcome again to ESI 211, Material Safety and Equipment Overview for Nanotechnology. And today we are working in Unit 2, which deals with infrastructure. And this is the outline for Unit 2. Infrastructure, what is it? Why do we need it in nanotechnology? And we covered that in Lecture 1. And then continuing into this unit, we have a discussion of facilities, and then a discussion of equipment systems, and that is has two thrusts, one dealing with vacuum-based systems, in which we get into discussions of vacuum systems, and another thrust that deals with non-vacuum-based systems. And this is Unit 2, Infrastructure, Lecture 2, Facilities. The outline for this lecture is, as you see here, we're going to have a brief introduction. Then we'll get into facilities and discussion of why do we need special facilities in nanotechnology. And then we'll talk about types of facilities, clean workstations, chemical hoods, would be another name in some cases, tunnel and bay structures, clean rooms, and then mini environments. So that's the outline we will be following in this Lecture 2 of Unit 2. So why do we need special facilities in the first place in nanotechnology? Well, we obviously need a place for manufacturing, so we need facilities. We need space, rooms dedicated to the manufacturing, so obviously we need facilities. But these facilities, as we discussed in Lecture 1, are very important to ensure safety for the workers, to ensure contamination control, and to ensure protection not only of the workers but also of the environment and process control. So let's get into some specific examples of facilities. And we start here with some facilities that you see on the right side. There's one type of facility. You see the robot, and you see the workstations over here. And here's another type. This is a glove box type, where the work is actually done inside control volumes defined inside these boxes, and workers put their hands in through these rubber openings to manipulate. So here's an example where all the manipulation is done by a robot in a very carefully controlled environment. Here's an example where the manipulation is done inside a carefully controlled environment with human hands going through these rubber enclosures which isolate the human from the inside. So we have all different kinds of facilities. These are two examples. We have clean workstations, an example which would be, for example, a chemical hood. We have tunnel or bay structures, we'll talk about those. We have clean rooms, and we have mini environments, and an example of a mini environment is a Smith box, and we'll talk about those. So let's talk about clean workstations, the first type we had in our list. So one approach in nanofabrication and synthesis is to create individual workstations, such as chemical hoods with air filters and non-shedding materials. So these are defined volumes, and a chemical hood is an example. If it has air filters, then it's a, we can call it a clean work station. This is a very simple type of facility. And the overall facility would be a room that has these workstations or these hoods arranged in it in rows, for example, so that products under fabrication can be moved from workstation to workstation without coming into contact with dirty air. Now that assumes you can move from workstation to workstation in some way without contaminating the product. And we'll get into that, how one can do that. But the emphasis here is on the workstations themselves. They may be in a clean room, we'll talk about that. They may be in a bay, we'll talk about that. Or they may simply just be in a lab, in which case we can't move products from one workstation to the other without contaminating the product. So we have the workstation. Hopefully we can do everything inside that workstation. If we have to move from workstation to workstation, then we have to worry about the environment during that transfer process. But let's focus on the workstation right now. These are volumes that have filtered air, carefully controlled filtered air, and the air is filtered through what are known as high efficiency particle attenuation filters. Of course, that's a long name, so it has an abbreviation. These filters are called Hepa filters. And so you'll find Hepa filters in nanofabrication facilities, in clean workstations. You'll find them in larger environments, as we'll discuss. You'll find HEPA filters in hospital and operating rooms. They're used anywhere you're trying to control the quality of the air, when you're trying to control what's in the air. Now, HEPA filters consist of large porous fibers which are folded into a filter holder in an accordion type of design. And HEPA filters allow a large volume of air to pass at a low velocity and have a filtering efficiency of 99.99%. So these are very, very effective agents for removing particulate matter of various sizes from air. The HEPA filter, just translating those words we just read into a sketch, you can see to show how a HEPA filter works, you can see the dirty air coming in here at the top, coming down into the filter, and the filter is that accordion structure that you see here. This is a schematic, of course, but that's the filter. And then that traps the particles, the pollen, the dust, the viruses, depending on the quality of the filter. And out comes then the clean air. So if we have a workstation, let's get back to this idea of a workstation. It has these HEPA filters to clean the air. And typically, this workstation, it's called a workstation, a clean workstation, or a clean hood, or if it's a chemical hood with this type of filtering, it could be called a chemical hood. It has the HEPA filter mounted at the top, and the dirty air is pushed through the filter. Now this isn't dirty air, this is just regular air. So I'm using dirty air to mean just regular air. It's pushed through the filter, and then it exits in a laminar pattern. And of course, laminar flow, just to remind you, is a flow that is like this, whereas turbulent flow is a flow that's like this. And so these HEPA filters are set up, and the whole workstation is set up to have laminar flow. Laminar flow is good because this type of flow causes mixing. This kind of flow over a surface will pick things up. This kind of a flow over a surface generally will not be as prone to picking things up. So you like the laminar flow. So the clean station is designed to have laminar flow. So it takes this clean air, and the air then passes over the work area in the hood. And another commonly used terminology for these hoods is vertical laminar flow hoods. So sometimes chemical hoods qualify to be included, but in general we're talking about a very clean workstation, a clean hood, and often known as vertical laminar flow hoods. So we have the hood, the air comes in, gets purified, and inside the flow is laminar, and then the air will come out of the hood. Now one has to be careful to avoid mixing. One has to be careful that if you're working with nanoparticles, for example, in here, the nanoparticles don't come out. You actually want to make sure that there's an exhaust system so that the exhaust doesn't come out, the air comes in, it's clean, you're working here, and the air is exhausted, and there's no flow of any kind of chemicals or particles out into the environment. So air is purified, the flow is laminar inside, you exhaust so that no contaminants of any kind come out into the room. So here's a picture of that, and you have the blower up top, the air is being purified, the air is coming down into the room. Here you show, here's the worker working, here the air is actually coming out, but you don't want something like that. You actually want the air to be removed and taken out. So you don't want that to happen, especially if you're working with chemicals that could be contaminants or chemicals that could be dangerous, or nanoparticles. So you want this to not come out to the human. You don't want that to happen. You want this air to be taken out and exhausted. Human works here. This is the work area. The air is cleaned and exhausted. Here's the glove box. And the glove box has, as we said, these rubber gloves, hence the name glove box, that the human puts his or her hands in and then performs some fabrication task inside this environment. And this is a different type of workstation. This is a very, very special type of workstation where you're not putting air into here. This is not using room air. It's not doing that, but it's using an inert atmosphere. And by inert atmosphere, we mean an atmosphere that perhaps is made up of nitrogen, maybe argon. This is an example of an inert gas. Nitrogen's rather inert. We know it makes up most of the atmosphere, and as such it's very inert. So the inert atmosphere inside a glove box could be something like nitrogen, could be argon, or another inert gas. So we're not using room air in this case. We're not filtering room air. We have a very carefully defined volume inside this box where we're doing work with our hands going through these gloves. This is a very controlled environment. So as we said, it uses maybe nitrogen or argon or another inert gas like helium, and it continuously circulates this inert gas between the glove box and a gas purification system. And the gas is purified to a value where it's less than 1 part per million H2O and oxygen. So very little moisture, very little oxygen inside this environment. So you see the equipment used to actually establish this kind of an environment. So basic components of the glove box, shown here in cartoon fashion, is the actual working space inside here, and then the glove ports here, and then the antechamber right here. The antechamber is, you close a valve here, you put your sample into here, close this back up, pump down with a vacuum pump. Here it is right here, so it can pump. It's a vacuum pump. And then once you get the vacuum low enough, you fill this with the same gas that's in here, and then you pass this through into the working site. So you need a vacuum pump here to pump this down. You also need it to pump down in here when you need to. So a vacuum pump is also an important part of this. You need it to evacuate the system, as we said, to pump the, when you're at the beginning, when you want to take air out and put in the inert environment. And you need it to pump the antechamber all the time as you're passing samples in and out. Obviously, by the way, with the antechamber, the flow of the sample is the opposite direction when you're bringing it out. And you need a vacuum pump for cleaning when you're regenerating the purifying system. You have to regenerate it because it traps the impurities and then you have to regenerate it so it's ready to continue to purify this environment. A very well-defined environment, constantly purified and kept isolated from the outside, but yet you can still put samples in, take samples out, and through the gloves, a human can then manipulate the samples. So, continuing with the discussion of the components, you have the gas purification system we talked about. Gets rid of oxygen, gets rid of moisture, has to be regeneratable. I guess that's a word. That can be regenerated. There's a good way to say it. Okay, and so that it can be constantly used to clean the environment. Then there's a control panel for monitoring the overall system. Control panel, the cartoon is up here. So basic operation is that this is sealed from the rest of the world, and you have the gas flow. The gas comes in, goes through the purifier, goes back into the environment. Remember the antechambers here, and samples are passed back and forth through the antechamber. And you have all kinds of filtering going on here, filtering here, filtering here. Make sure there's no aerosols, no unwanted gases, so there's no nanoparticles flying around in here of any sort. And then you have valves, which are usually electro-pneumatic type valves, that is, electrically activated pneumatic valves are commonly used. And the valves are here to open and close different systems as you're operating. And then you have cooling, because running all this equipment generates heat, so you have to make sure that you get rid of any of the heat generated in the actual processing, and that's another aspect of the piece of equipment. Now the purifier unit works by chemically binding things that you don't want in the air, such as oxygen and water vapor. And so that's how it works, and it removes all gases that operate, that interact with, rather, copper or copper oxide, and it traps gases in a molecular sieve. Blower, the circulation unit that we talked about, causes the circulation of the gas flow, and it's encapsulated in a vacuum-tight container. So this is, as we said, a completely sealed system, and a circulating system. Now, how are glove boxes used in nanotechnology? Well, they're used in a lot of different ways. For example, in nanobiotechnology or biotechnology, they're used to allow folks to work with anaerobic organisms or anaerobes. These are organisms that don't want oxygen, or that they don't need oxygen, and actually oxygen can be often detrimental to them and kill them. So obviously, if you're working with that kind of an organism, you don't want oxygen, and a glove box is great for that. If you're working with materials that are oxygen or moisture sensitive, glove box is wonderful for that. It's wonderful for doing inert welding, that is, welding in inert atmospheres. It's wonderful for working with things like lithium batteries, because you need a moisture-free production environment. So anytime you need to really carefully control the environment, the glove box is very, very good. And you don't need a clean room. You don't have the open hood kind of situation. And so a glove box can be a very interesting type of facility. And you can deposit films in a glove box. There's no reason why you can't put an evaporator or some sort of a deposition system in a glove box. And then you can produce very clean, very contamination-free films of aluminum, copper, all kinds of organics, P3HT, PCBM, which is an organic used in photovoltaics. So you can produce lots of materials inside a glove box. For example, aluminum often, well, not often, but very easily forms an oxide, and that's not going to happen if you do the evaporation in a glove box. Of course, it won't happen if you do the evaporation in a vacuum system, and if you do the evaporation in a vacuum system in a glove box, it's surely not going to happen. So, glove boxes can be interesting for contamination-free processing. They can be used to allow individuals to work with hazardous materials, because the material is really sealed off from the rest of the world. And an example of a hazardous material would be high biosafety level pathogens, and even radioactive materials can be worked with in a glove box. Now, the tunnel bay concept is a different concept. So we've talked about workstations, we've talked about glove boxes. So I'll put little gloves on the glove box. So this is a workstation, this is a clean hood rather, or a clean hood or a workstation. This is a glove box, which is also a workstation. So let's say this is a clean hood, this is a glove box. A tunnel is when you define some volume. So this is a small room, and you put the workstations in this tunnel. Maybe they're outside, and you just access them right here. The rest of the machinery is outside. Or maybe they're actually inside, like this. Or maybe they're a mixture. The way I have it drawn here. Here I have some of them outside, except for the interface. Here I have them inside. But this volume, this room, is called a tunnel or a bay. And it allows more stringent particle control. Remember when we had a couple of clean hoods and we talked about taking a sample and moving it to another clean hood? Well, if we don't have a controlled volume here, if this isn't controlled, then we're going to get contamination if we do that. So one way to avoid that is to define this volume, this tunnel or this bay, where we control the environment and we're able to move samples from one workstation to the next workstation. So it gives us stringent particle control, and we can then have the individuals here dressed in cleanroom garb, and we can avoid human-induced contamination. So we can avoid having dirty air here because we're filtering it, and we can avoid having human contamination, and we can move the samples from, say, clean hood to clean hood to clean hood. We can even have a glove box in here if we want. So this allows flexibility. So this is done by creating these volumes, that is, dividing the fabrication synthesis area into clean regions called bays or tunnels. These words are used pretty interchangeably. Then the workstations are located in these bays or tunnels. In this design, clean air enters into the bay or the tunnel from above by Hepa filters. So you have your Hepa filters on the top of this area. Then you have your workstations, which may have their own Hepa filters. And so you're really carefully controlling the environment. In this way, materials are less vulnerable to personnel-generated contamination. And they're less vulnerable, well, they're not vulnerable when you carry them from one sample to another, from one workstation to the other. They're not exposed to dirty air. So this is a rather good way to handle that situation. However, it has a downside. Obviously, it's more expensive because you have to define this volume. You have to have the filters in it. Those are expensive, and it's less versatile than a clean room. A clean room is a large volume, and a clean room gives you all sorts of versatility. So the tunnel bay approach is expensive, but it allows you to have better control of the environment. So it's more expensive than the hood, but it's not as versatile as a clean room, but it's less expensive than a clean room. So like everything else, there's trade-offs involved when you use this type of facility versus just the workstations, that is versus just the clean hoods, or versus the next more complicated system, which is the clean room. So the tunnel bay design, as we said, is workstations. The worker is in this tunnel, and there are multiple workstations usually, and then the HEPA filters cleaning the air coming in, as well as usually HEPA filters for the clean hoods, the workstations themselves. Now, the cleanroom approach is the third in our approaches. We talked about the clean stations or the hoods. We talked about the tunnels with clean stations with workstations and hoods inside them. We talked about the glove box, which is a type of clean station, but very, very carefully controlled environment and isolated. Now we're going to talk about the clean room. So simply stated, a clean room is a volume of room where contamination is reduced and controlled. And a clean room is designed to minimize contaminants. Now again, the clean rooms are classified by a classification scheme we introduced in Lecture 1. And this classification scheme, as we mentioned, comes from Federal Standard 209D. And just to review, if a clean room is Class 1, then there are no more than 35 particles of 100 nanometers diameter or larger. And of those 35 particles, there can't be more than 8. There has to actually be, it can't be more than 8 that are 200 nanometers in diameter. And it can't be more than 3 that are 300 nanometers in diameter. And there can't be more than 1 that's a half a micron, that is 500 nanometers in diameter. And there can't be any up here. And so, again, let's remind ourselves that this is all defined, these numbers all refer to what's found in a cubic foot. And then we have Class 10, Class 100, etc. Cleanroom contamination, we've discussed this in Lecture 1, but just to review, humans are the biggest source of cleanroom contamination. A cleanroom operator, even after air showering, and we'll discuss what air showering means in a minute, can give off between 100,000 and 1 million particles per minute. And this number increases when a person's in motion. 2 miles per hour, just to give you an idea, a human gives off up to 5 million particles per minute. So we talked in Lecture 1 about putting that person inside a clean room garb, so they could wear that clean room garb in a clean room. They may even wear it in a tunnel or a bay kind of configuration. And this way, the human is isolated from contaminating, at least to an extensive degree, the environment. And then the processing equipment is the second biggest source of clean room contamination. The equipment itself, as we mentioned a couple times, can be a source of contamination because, for example, you may have, let's say you evaporated aluminum in this evaporator. Then the next step, you evaporated something else, let's say X, just to be more general, but there's still aluminum on the wall, and X might react with aluminum and perhaps produce something that gets into the environment and gets on your substrate. The point is, the equipment can be contaminated, and that can, in an uncontrollable way, and that can affect subsequent processing. Or perhaps this evaporator uses, it's a diffusion pump, and there's diffusion oil involved. The oil can get into the chamber, and that can get onto the sample. So we'll get into that in detail, but processing equipment is the second biggest source of clean room contamination. For that reason, to try to minimize that, often equipment is placed in the chase area of a clean room. So here's a clean room. Chase area is what you call this volume around the clean room. Let's suppose this is where you walk up and down in front of the clean room here. This is the clean room. Maybe there's glass here and you're going to look in. This chase area, as we said, you may have workstations. in the clean room, but often you put the workstation out here and just the interface with the workstations here. Or maybe you have that evaporator we were talking about. Maybe it's back here with just an antechamber for putting samples in and out in the clean room. So often equipment or parts of the equipment are actually put in a chase, this area around the clean room. Many clean rooms, you also use the space underneath the clean room for equipment. So humans have to be, getting back to humans, as the number one source of contamination. We said equipment was number two. They must be isolated as much from delicate materials and equipment. People must wear clean room garments, the bunny suits we talked about in lecture 1 of this unit 2. And the bunny suit, as we know, consists of key elements like hoods and face masks and overalls and coveralls and boots and gloves. And then, of course, for safety issues, gloves have to address safety. We may have to wear special gloves. We may have to wear a apron of some kind for special chemicals. But in general, clean room garments, the bunny suit has these elements. Now, when you gown up, when you put on all this equipment, you have to follow a procedure to do so, and also, as we said, in addition to this gowning or the standard gowning elements, you often have to have special additional equipment for certain processes. We talked about special gloves for chemical handling. We specified aprons. You must always wear safety glasses in these facilities, whether it's getting back to a hood, a clean station, glove box, or whether it's a bay or a clean room. You must be wearing safety glasses in these facilities. On the gowning protocol, just to go over that, this is a very simple type of gowning situation. Perhaps you're working with a workstation and the samples never come out into the environment. This is a more stringent clean room attire, and this perhaps can be used in this would be used in a higher class clean room. This would be used as a lower class clean room, maybe perhaps a class 100,000. You have to, of course, wear all these different things, and you have to, in the clean room, and you have to begin, generally speaking, you begin with you put on the shoe covers, and then you progress through to covering the head. So you put on the shoe covers, the face mask, and the hairnet, and the hood, and the bodysuit, boots, gloves, goggles. The air shower. This is the air shower we were talking about. It's a shower, but not with liquid. It's a shower with gas, and so you see the showering to blow off any particles that may be present even after you've put on the full attire. So the clean room is a real special environment. You work really hard to get the humans ready to go in, and you work really hard to keep the equipment such that it is not contributing to contamination. It's an open fabrication synthesis area. It's a large volume. It's a room. The air filtering, again, is accomplished by these Hepa filters that we discussed. They're in the ceiling, so the air comes in through the ceiling and generally goes out through the floor to give a continuous flow of clean air. The clean rooms are designed to try to make that flow laminar, because we don't want mixing, as we said. We want laminar flow. We don't want turbulent flow. This kind of flow gives rise to mixing, mixes things up. And this continuous flow through the Hepa filters, through the room, out the floor, allows for continuous recovery, and you can keep the room very, very clean as you want, depending on what clean room level you're striving for. So the flow is in, through the room, out through the floor. The air is filtered, and then back in again. So this is air. Remember in the glove box, this was a small glove box, and it was an inert atmosphere doing this. This is air now. This is a large volume. This is the ceiling. This is the floor. The air is constantly purified. If the facility is class 1, the air is turned over, that is exchanged every 6 seconds. So you get an idea of what kind of investment and equipment is involved. You get an idea of the size of the blowers and the filters that must be present to change the air every 6 seconds in a class 1 facility. Here's a good schematic of a clean room, and you can see the plenum chamber up here where the air is collected, the flow through the Hepa filters, the clean room. You can see different pieces of equipment. Maybe there's different workstations here. Different things are being done, and the air flows out through the floor, goes through the service chase, and then gets blown back again through the clean room. And then, of course, there's the fresh air makeup taking place. And as we said, you want to make sure this is laminar flow to minimize mixing. So the traditional clean room today is what's called a ballroom. That is, it's this large volume that I mentioned. Then there is perhaps it may be divided into tunnels. Remember we talked about tunnels. So this may be a tunnel here. This is a wall. This is another tunnel over here, and you can go back and forth. The whole overall structure is the clean room, or there may be no bays, or these are bays or tunnels. We said they may not be present. It just may be one open ballroom. And every clean room is a trade-off between cleanliness and cost. But they all have a basic design: a sealed room that has very careful control of the air, and the air is clean through HEPA filters. It's built out of materials that are non-contaminating, so a great deal of thought goes into the materials. Generally, the materials are designed to protect from electrostatic discharge, which we briefly mentioned in Lecture 1. Everything is designed so that the facility, the clean room, doesn't contribute to any kind of accidental contamination. And then, of course, you need to think about vibration, because we have those blowers, and you have to make sure that there's vibration control so that you don't have things shaking. And here you are trying to make something at a nanoscale, and the amplitude of the vibration is well above that. And so you have to give considerable thought to vibration issues. Clean room elements. Well, lots of things go into a clean room. Lots of things used to build a clean room, and you have to worry about adhesive floor mats, so that if someone is not carrying material around on their shoes. Remember, the shoes have shoe covers on, but it's still possible to pick up something. So adhesive floor mats are commonly used. You have to worry about electrostatic discharge. We talked about that. You have to have a gowning area. You have to have proper door design and pass-throughs. Let's just talk about that for a minute. So here's your clean room. You need, let's suppose we're looking down. You need a gowning area out here, someplace where you gown. You need perhaps a place where you get a shower. You need pass-throughs so that people can pass things out of the clean room if they want, and pass things into the clean room if they want. So you need these sorts of things. You of course have to worry about fire escapes and door arrangements. Then you also have to think about making sure the doors are big enough to be able to bring equipment in. So you need some doors somewhere for both fire exiting and also to bring in new equipment, take out old equipment. And then of course you have to have a chase around, and then you have to have workstations that may be in the chase with just interface region, or maybe in the clean room. It can be with a ballroom design, as you see here, or it can be made up of bays. Bay here, bay here, and have all these different options. You have to control the air pressure. You have to worry about maybe shoe cleaners out here. You don't want to, even though you have the shoes covered, you might want to make sure they're clean before a person puts something on their shoes. Often in clean rooms, folks actually change their shoes. There's special shoes just for the clean room. Then we have the air shower we discussed, glove cleaners, service bays. Service bays are also called, as we said, service chases. So this is also called service chases. Now there's another approach to looking at facilities. And this other approach is to say, well, let's move. Look, what's the problem? The problem is we can define really clean workstations, but then as soon as we move something from one workstation to the other, we're in trouble. So we can use bays, or we can use a full clean room, or perhaps what we should do is have some kind of a mini environment, and that hooks up to one workstation. We do our work, we put the sample in the mini environment, and carry the mini environment over to the next workstation, and then put the sample into the next workstation. The sample, that is the object we're working on, the thing we're doing fabrication with. So rising clean room costs, and clean rooms are expensive. So for example, if I look at the latest numbers for building clean room facilities for microelectronics, of course microelectronics today really should be called nanoelectronics because the transistors are so small. But if I look at the costs of building facilities for microelectronics, by the way, those facilities are called fabs. So now we're going to talk about a facility which is the clean rooms plus the equipment. These are costing about $3 billion per facility. So this is really expensive. And so that has spawned the idea of maybe isolating materials in as small an environment, as possible. So how do you put these different small environments together? How do you say you have a bunch of workstations? These are very carefully controlled environments. How do you move the sample from here to here? That was a problem we faced many, many view graphs ago. We talked about the contamination from people and air that occurs here. That led to the bay concept. That led finally to the clean room. Is there another way to do it? And the other way to do it is this idea of transporting the samples from here to here in a special environment. And one example of that is an approach developed by Hewlett-Packard, which is called the Standard Mechanical Interface. That is the SMIF, or it's usually affectionately called the SMIF box. So the SMIF box, or the SMIF system, has three main components. It has a pod or a box, hence that's why it's sometimes called the SMIF box, for the transportation of materials. And then so you work in a mini environment that's very, very clean, and then you move to the next mini environment using the SMIF box. And the mechanism for extracting and unloading materials at each successive processing station is rather interesting, and this mechanism for extracting and unloading materials at each successive processing station, that is, as we go from this processing station to this one, we have to use a SMIF box, and we have to make sure that we put the sample in, but no contamination occurs, and we can't contaminate this, and then we bring it over to here, and we put it here, we transfer the sample in, no contamination should occur, nor should we contaminate this, which we are going to use again. So we have to worry about all these things. So in pictorial form, we can show, for example, a bunch of wafers in a cassette here. So these wafers undergo some kind of process in processing chambers here. That is something that is going on in a processing, and they're this constitutes a workstation here, constitutes a very clean mini environment. And now we want to move it to another one. So what do? Well, you have this load lock, which is another name for antechamber. You'll see folks use load lock, antechamber. This is a region, a transfer region. We ran into this with the glove box. So load lock, antechamber, that's a region where we're going to do the transferring. So up comes the SMIF, that's this. It docks here. There's no leakage. The sample gets transferred into here. This is pumped down by the vacuum pump, and then the sample's passed in, and the processing is done in these workstations or workstation. Very controlled environment. And then when the processing is done, it comes out, comes into here. Another SMIF box is docked here, perhaps the same one. The SMIF box and this region are pumped down again. The samples come through, go into here, and then this closes, and you're ready to repeat the process. So this is a way of using these isolated pods with a vacuum. Create a vacuum in here, you pump down, or you may pump it down and backfill with an inert atmosphere. Remember the glove box, we pumped it down initially to get it going, and we backfilled with an inert atmosphere, which we then continue to cycle. Well, here you can either pump down, keep a vacuum here, or you can pump down and fill it with an inert atmosphere as you go to take this and move on to the next workstation. So this is a workstation with different process chambers in it, perhaps, and we're doing this very controlled environment. We're doing our work here and then transferring to the next workstation. So we don't have to worry so much about the environment out here in the room. And often you'll see this done in industry with robots doing all this work. This is all handled inside here with robots, and even robots carrying these transfer units back and forth from workstation to workstation. So the SMIF box system has the advantages of very, very carefully controlled temperature and humidity, and very, very careful control of the contamination, which means you're going to get less yield loss. And we talked about how important that is. Yield loss equals money loss. And so this kind of approach means you don't need to depend so much on clean rooms, but you can still maintain a very, very stringent contamination requirements. There's problems though. The pods can be heavy. You have to have robots often to handle them, and then that gets complex. Now you have to worry about robots. They're not going to contaminate, but you have to obviously maintain and control the robot system. So, like everything else, there are trade-offs. Well, to summarize what we've done, we have just completed Lecture 2 of Unit 2. And Lecture 2 has covered facilities, the facilities used in nanofabrication. And we've looked at a lot of different kinds of facilities, and these are all part of the infrastructure needed for nanofabrication. And the outline we followed in this Lecture 2 was we introduced why we need facilities and some general thoughts on the need for protecting workers, the need for protecting the environment, the obvious need of we just have to have some place where we do this work, the need for controlling contamination, and of course in Lecture 1 we discussed how contamination affects yield and product function. So we need these facilities, and then we went over the different types of facilities, some common examples of facilities. We talked about clean workstations. These can vary from the simple chemical hood all the way to glove boxes, the different types of workstations. They can be complex in the sense that there could be inside a workstation a number of different pieces of equipment. So a workstation may be complex. It may have a robot inside it moving things around to carry out the processing. So we started with just simple hoods and talked about the air flowing through HEPA filters into the environment, and then discharging the air, making sure that in the simple hood type, the worker can access the area, the volume inside the hood, but trying to control any nanoparticle or chemical flow back out of the hood. And then we talked about tunnels and bays, where we assembled workstations into a volume in which we then controlled the contamination. And the reason we were driven to look at this tunnel bay idea was we realized that often we may need to move products as they proceed through the processing flow. We may often need to move them from workstation to workstation. And how do we do that? So we came up with the idea of these tunnels or bays, which are cleaned again with HEPA filters and have a very well-defined, clean environment in which we can move the samples back and forth. Of course, we had to worry about keeping the humans properly attired in those volumes, but we discussed that and the whole idea of clean room garb, which we've introduced as early as Lecture 1. Then we talked about looking at even more complex volumes, and that was larger volumes, larger rooms, and we introduced the concept of the clean room, in which there may be bays which interface with one another, or there may be no bays. It may be a ballroom style clean room, and there's multiple workstations inside that clean room, and the clean room has a very carefully defined, very carefully maintained environment. And we talked about class 1, class 10, class 100, and so forth, and talked about how that's maintained with, again, flow through HEPA filters and constant exchange up to 6 times a second in class 1 clean rooms. And then we moved to mini environments in the Smith box, and the idea of, well, maybe we can address some of the cost issues of making clean rooms by defining small environments which we can use to move samples from workstation to workstation. And of course, we then discovered that there are some issues here too, and those perhaps usually center on robotics and the cost of running a robotic controlled or a robotically enabled system. So these are things we've covered in Lecture 2 of Unit 2. Look forward to your joining us again for Lecture 3.